Hi everyone, in this video I'm going to talk about my final year project, which is about improving the accuracy of a low quality eye checker. So I will start from data collection part, and at first let me introduce the calibration process. Since the software eye checker is originally trained for mobile phone, but now we want to use it on computers, so we have to do a calibration. Here you need to specify the size of the screen, and then the program will display some points on the screen. You can have a look at that. At this time, you need to look at those points on the screen, and the web camera will take images of your face, and later on the images will be used to do calibration. So now, assume we already have the data. Let's go to the synchronization part and try to synchronize two data sequences. At first, since in my data collection, I perform data collection on the professional eye tracker, and at the same time, I use a camera. I use my mobile phone to take a video of my own face, and later on, this video will be used to extract the features for the inputs of the software eye tracker. So, as long as I have a video, I can extract a WAV file from the video, and also I can plot the audio frequency chart. Maybe this chart is not clear enough, so let's zoom in this part, and we can get this chart. So you can see that there are some patterns for the audio frequency because it's generated by a program from the professional eye tracker. So for this point, it's the ending point for the audio waves. For this point, there is already a timestamp for the professional eye tracker as it's generated by it. And also, and now by finding this point on this chart, we can have another timestamp for the video. So we can use two timestamps to synchronize two data sequences. And now we keep zooming until we find this point and we get an index. Then we can use the index to calculate the time in seconds for the video. And finally, we can get a synchronization index. So later on, we can use this number to synchronize two data sequences. So this number refers to the latency for the video comparing to the professional eye tracker. Now let's extract the calibration points and plot them. So you can see that for those images, in those images, I'm following a 9 points calibration pattern, and then a 4 points calibration pattern, and another 6 points calibration pattern. So in total, there are 34 images, which means 34 calibration points. So now we can jump into this file to process them. At first, you need to import Cafe and some useful libraries. Here is about the setting of the Cafe model because the software eye tracker is trained using Cafe. For this part, later on, if you want to use it to do eye tracking, you don't need to modify this part because I already specify all of the parameters. And also define some functions. So now, at first, let's generate a calibration model using the 34 points we get before. And we just use those points at the inputs for the cafe model. and we get the results. So this results, the unit of it is cm, so it's for mobile phone. And now we need to use a linear regression or ridge regression, depends on the number of calibration points. We use the regression to map the value into pixels. So the output of the regression model will be the coordinates for the computers. So by now we already finished the calibration process, and we get a software eye check for computers. In addition, I also plot the raw predictions in CM, so it's for mobile phone. If you have a look at this, you may find that it's irregular, but actually it's a 9 points calibration pattern. So you can find that the error is significant. So if you want to use this model on computers, you have to do a calibration before you use it. Afterwards, we can extract all of the frames from the video and start a prediction. Before forget to tell you, before that, you can use the program I write to extract all the frames and the features from the video. So you don't need to produce the inputs for the software I check by yourself. Also, those codes are good formatted, so you just need to change some parameters such as the length of the video. And here we make a prediction for all of the video frames. Afterwards, you may want to store them using Pico, because later on, when if you want to reuse the data, you don't need to redo the prediction. So now let's try to synchronize the two data sequences by using the index we get in the synchronization file, and we use it to do synchronization and get the results. Afterwards, we also store the file into Pico. And now this part is for producing the inputs for the regression model, which means for every gaze point, we will produce an image applied with Gaussian blur. It's like this. So they can be used as the inputs for the CNN regression model. One thing to note is that for this part, you may need to specify it because it's the ratio of the screen. You have to find the parameters for your own screen and specify it here. And then we also produce a continuity list. So what's a continuity list? Let's have a look at the data sequence from Toby. Between these 2 points, you can see this index is 3 and then followed by 13. So between these 2 points, there is an interval, and in this interval, there's no points, eye gaze points available, which means I may did an eye blink in this interval. So we have to use the continuity list to store the information, because later on when we use the time series model or regression model, we have to know the information about continuous points. So here we define some useful functions for get the differences between two data sequences. And now let's have a look at the time series model. So this is a Kalman smoother with a maximum window size of 30, which means assume now we have 20 continuous points and followed by a eye-blink period. So in this situation, this program will just use the 20 points to start a Kalman smoother and make prediction on the 20 points. So maybe after this period, there is another 40 points like this. So this program will just use the first 30 points to relaunch a Kalman smoother, and then use the rest 10 points to launch a new Kalman smoother. So in this way, the model can be real-time even you do many and many eye blinks, because it will not wait for you. So let me also show you the results of this Kalman smoother. So you can see that the improvements is not significant. After all, it's just an unsupervised learning model, so it didn't produce a very good result. Maybe let's have a look at this model. So this model is another Kalman smoother with a fixed window size, which means assume now you have 20 continuous points, and in this model, the program will wait for another 10 points, even during the waiting time. You did a lot of eye blinks, but the Kalman smoother will just wait until it gets 30 points, and then it will start a Kalman smoother to compute the predictions. In this situation, the results is better. However, if we want to use it real time, we cannot use this model, because sometimes if people do many eye blinks, then this program will wait until it gets enough points. So in this situation, the latency may be significant. Afterwards, let's also produce the saliency map of all the screenshots, because for every eye gaze point, there's a corresponding screenshot, which means when I look at this point, the screen is like this. So we also compute the saliency maps for all of the screenshots. Later on, those saliency maps will be used as the input of the salient regression model. And now let's move into this part. Since in the previous file, we already prepared all of the inputs required by the regression model. Now we can we just need to launch the model. At first, we also specify some libraries and path, and define some functions. And then we load the training data and testing data. So here I use one data set for training and another one for testing. You can have a look at here. It's the original accuracy of the training data set, and it's the original accuracy of the testing data set. Here is the model structure. You can see there are 3 convolutional layers, followed by 3 fully connected layers. So now let's start the model and try to feed the data using 5 iterations. Here is the final result. So you can see that compared to the original accuracy, there's a small improvement. However, this model cannot be used in real time because it takes a lot of time to prepare the inputs for this model. So in the future, I may want to improve this model, and the main concern is to make it faster. In that situation, we can use this model real time,